All right, what is up, everyone? Welcome to week 62 of Chill Kernel Hacking for Fun. Hope you're having a great day. I will be working on exercise 7 and 8 from the MIT course, which is continuing with networking for the operating system. And last time we were working on exercise 7, and I had just finished adding a really bad system call to the OS. That was just a basic proof of concept for what it sort of would look like, because I'd just finished implementing basic transmitting from the driver. And the idea is to now expose that very raw transmit functionality to user space somehow, so that the user space network stack can ultimately make use of it and send packets. Here's what it looks like. So first off, it's just a lot of it is a lot of plumbing, but the actual system call is right here. And it's pretty much the worst system call in the world. It just takes a buffer and a length and calls the driver's transmit function with that buffer. And it does validate the pointer. The pointer given to us by user space is a valid pointer, but it just is a straight pass through into the driver function. And this driver function has a lot of limitations, which are not in this commit, but that's just, I'll hop over to the code now. The driver function has an incredible amount of limitations. It can only handle buffers up to a fixed size, which is 128 bytes at the moment, because of the extremely naive handling of the NIC ring buffer that I'm doing. So it can only handle fixed sized amounts, basically, which kind of sucks. And yeah, maybe we can do something about that. I still really have no clue what the actual idiomatic way to do this is. It might be possible that I need to reference some of the other OS stuff. Like, I'll just maybe pull up quickly. There's this XV6 from 2022, and it also has a bit of information about this. And yeah, they have this, I don't know, different way of handling it. I don't know what this mbuff thing is, but they use some kind of dynamic allocation for that. Memory buffer is maybe what that stands for. So maybe we can reference that. We also still don't really have a good memory allocator in the OS. So yeah, maybe that's a problem. But anyway, it's the system call is a straight pass through directly into this driver function. Yeah. And that's pretty much it. The rest of this commit is just system call plumbing, which is actually pretty onerous. There's just a lot of boilerplate that's needed to add a system call and then expose it to user space through the user space C library. And that's what we're seeing here. And I just named it network transmit because I don't know what else to name it. Yeah, so that's where we left off. And moving, so that's kind of a shaky implementation of exercise 7. exercise 8 is actually trying to use that. So let's just take a moment and read through this. Transmitting packets, network server. So now that you have a system call interface to the transmit side, time to send packets. The output helper environment's goal is to do the following: accept some IPC messages from the core network server and send the packets accompanying these IPC messages to the device driver using the system call. The IPCs are sent by some function in this file, which is part of somehow the glue that's between the lightweight IP stack and the rest of our OS. Okay, that's literally what it says. And JOS's network system. Each IPC will include a page consisting of a union NSIPC with the packet in its struct C. Okay, and this is just kind of how the IPC system works. It's a shared memory IPC. It's yeah, which is one of the simplest things to implement. And two different user space processes can basically send messages to each other, each and transmit data via shared memory. And so I suppose the IPC message from pictures here. The IPC messages come from the core network environment, and then they call into the output helper environment. So specifically, this is what we're looking at today, and there's this IPC message that is sent. Yeah. Okay. And then there is a length and some data, and apparently there is this weird C trick where you can have unlimited data or something, arbitrary length data like this. Okay. Be aware of the interaction between the device driver, the output environment, and the core network server when there is no more space in the device driver's transmit queue. The core network server sends packets to the output environment using IPC. If the output environment is suspended due to a packet system call, because the driver has no more buffer space for new packets, the core network server will block. So basically, if this system call blocks because this buffer is full, then this process will block, which means this process will block. And those are some of the IPC details that I'm not fully remembering about this blocking behavior. But apparently, I suppose sends also block. We would need to go back. Maybe it's not that hard to find this out, but we would need to go back into, I think, is it lab 5? No, lab 4. Block. What? So here is a bit of documentation about how the IPC system works. To receive a message, you call this, and then you get descheduled, which means you block. To send a value, call this. So I was thinking actually that sending would not block. actually receiving. Then it delivers the message, and otherwise send returns this to indicate that the target environment is not. Ooh, maybe it's useful to just actually look at the code. So, I mean, probably syscall.c send ipc try send. Right, if they're not, so basically the state of whether a process is open to receiving is stored in its like task struct sort of thing, and we check that, and then we do some like consistency checks or something. And we do checks on the value received from the process. Otherwise, we look up the page of memory that sits in the sending process. And then we insert it into the target process. And return. And then we set all this up. Then we like say it's not receiving anymore. We store who sent this, some value, some permissions thing. Yeah, I don't quite remember this stuff. And then we set the process that was blocked and waiting to return 0. So there's no queues or something or anything like this. It's just like completely synchronous, basically. And it just does it, and then basically sets the other thing to wake up. So, so no, this shouldn't. This system call does not block. What potentially blocks is user space, which has some wrapper. You see. So there's this user space wrapper called IPC send. And that's sort of the thing that is pseudo blocking. You call this and it will sit there until it succeeds, basically. And that's kind of the blocking nature of this. System call doesn't block, but it just like busy waits, and it like deschedules itself or something to be CPU friendly. But okay, and so that's kind of the important part. So going back to our network stack, this network stack component is going to be calling IPC send, and it will loop until it succeeds. So that's effectively blocking. So that's what they mean by this thing. I'll just make a copy of that for reference. However, in my implementation, there is no blocking. If this ring buffer is full, we simply return, which is the simplest thing to do, is just bail out. You just call this, and we just don't do anything. We can see that here. If the buffer is full, we just like return some error code and do not do anything with the data you sent, which puts it sort of up the pressure on here to monitor if the system call works and retry it or something, basically. But the thing is, I don't actually really expect the ring buffer to ever completely fill up because of how we're running it in QEMU, which is obviously different than how hardware would behave. And with QEMU, from what I understand, as soon as you write to the tail register to kind of to do the final action of submitting a descriptor to transmit, I believe QEMU basically just synchronously processes something in that moment, potentially actually blocking like the OS. Like the OS runs, it does a memory write, and that memory write blocks, and then QEMU goes and synchronously processes a bunch of stuff from the queue, and then you keep going. And because of that synchronous nature, I don't actually know if it's ever possible to fill up the buffer, because every time you add something new, it's just going to process stuff. And so you'll never have the real life behavior where potentially you enqueue way too much and the other side, the hardware, was doing something, we don't know what, and it wasn't able to keep up with the transmission of how fast we were sending it in. And so because we don't have this asynchronous nature, I don't actually think the filling up thing is ever going to be a problem, which is just a nice simplification we can, for the moment, rely on, I believe, because we're using QEMU. If we wanted to make this actually work on hardware, it's a different question. We would actually need to do a much better job with this. Okay. So kind of read through this. Okay. Now it says implement net output.c. What I am interested in is how this glue works, though, because that also informs the system call interface. It's sort of tough to write an interface where you have no idea what the client looks like, and that's kind of what I did. So I expect we will need to make some changes here. At a minimum, probably it would be nice if we could support arbitrary length buffers. Like if user space could submit a buffer greater than 128 bytes, basically. That would probably be pretty nice. So that's at least one thing to be aware of. I'll just take a quick palm tree break. Be right back in 20 seconds. Okay. Cool. Before I go in and rework this system call, which I have some ideas for, just quickly. So the obvious idea is to do some kind of loop here. The easiest and most simple thing for the moment is perhaps to just retain this constraint that we can only pass buffers of length 128 into E1000 transmit, and then just chunk up the given buffer into that amount, basically. Maybe I'll just write some of this stuff down. So right, the problem is this whole thing. Problem. Syscall has a fixed max of 128 bytes. That's annoying for callers. Some solutions. We could make syscall. That's just arbitrary buffer in chunks. Retain 128 byte fixed constraint. Another solution would be maybe dynamic memory allocation. And so instead of retaining this constraint, we actually rework things and genuinely allow, instead of fixed 128 bytes. Yeah, instead of fixed 128 bytes. Then yeah. I also need to take a moment to really understand, I guess, from a mem copying perspective, what is really going to happen here. So actually, this is kind of interesting as it happens now. There isn't copying. Okay, wait, there is. No, so what the copying happens here. We receive a buffer, we mem copy it into the backing buffer. That's what happens. And then that goes out for transmission. Maybe I can try to illustrate this some more with some rectangles. So let's say, so basically we have a couple backing buffers, and then we also have these descriptors. And currently it's very simple and backing buffer fixed size. And yeah, each descriptor is associated with a backing buffer. And then let's say a system call is made. So user space allocates some NIC buffer. I'll just present this like this. User space allocates some buffer of memory and passes it into this system call. And then the system call basically after validating the length and stuff like this, it determines the backing buffer for a given descriptor. Let's say it's this one, and mem copies it into there. So now there's two copies of this data. There's one that's owned by user space, and then there's one that lives in the kernel. Okay, so just to kind of level set, that's how this thing works currently. Okay, so instead of doing things this way, specifically instead of having this fixed region for every single thing, we could imagine an alternate world where yeah, these are like dynamic. So it's not like there's associated buffers, it's just like on every system call, we allocate a bespoke region for whatever was passed in. And then we point this to there. We do the transmit, and then the net, and then yeah. Then let's say we go around and we fill all these other descriptors. We come back around. It's time to we want to reuse this descriptor, but it has a pointer to this thing. We then free that buffer and then start over and allocate a new one. I believe this is actually how XV6 works. Something like this. This is the reason. Something like this. And actually another reason I believe this is because if we go to the more recent version of this lab from 2022, it's slightly different, but they give some hints, which I'm going to screenshot. And specifically, it talks about this. Use free to free the last dynamic allocation that was transmitted from this descriptor, and then point the descriptor at this, at the past buffer. The difference in here is that somehow in this version of the OS, the function is past the buffer, like a kernel buffer already. And we can maybe check out what the call site looks like. So even here, we already I don't know, even here, we already have it passed. Here is the actual call site, and it's just this chain. The interesting thing, it seems here in this kernel, they don't use lightweight IP, I think. Okay, it just bubbles all the way down. And at some point we are going to see, yeah, this is sock, right? So this is probably kind of close to the syscall boundary. There's some kind of socket implementation, it seems. And when you write to a socket, yeah, you write to a socket, they allocate some memory, and they copy the memory from user space. Copy in and buff puts, I don't know. I have no idea what this does. But I can kind of just assume that it's copying data from user space into this kernel buffer. And apparently there is some constant that is being used, which is actually 128, which is kind of interesting. Because that's the same as what mine is. I think they are dynamically allocating a 128 byte buffer, which means that if you try to pass more than that into this socket, it will fail. So that has the same problem as my OS currently, which is that user space needs to take care of this. That's kind of interesting. Maybe I'm misunderstanding this. Maybe maybe this is actually not the size of the allocation. Maybe it's something different, but that would be kind of weird. Mbuff, it's a packet buffer, headroom. And so this is interesting. They allocate something, and it is sort of this linked list kind of thing. Wait, next. Okay, I'm not sure what this next thing is, but size of. This smells like a fixed size buffer to me. Mhead equals buff plus headroom. And so I guess the headroom is some area reserved maybe at the start of the allocation, actually. Which is interesting. Then they point head at there. Mbuff size, I'm going to actually, I think that is some static size. I would love to see the struct definition of struct mbuff, if I can find it. Right here. And okay, here we go. So this is kind of instructive. So XV6 risk 2022. Some kind of 2K buffers allocated on every socket, right? Some mysterious headroom concept for some reason. Yeah. But ultimately, it is also, at the end of the day, a static size buffer. They don't dynamically allocate a buffer every time. So that's interesting. Which makes me feel a little bit less bad about my current way of doing it, where it's just this fixed thing every time, because basically they have the same thing. Except they are, instead of this being just really statically allocated in memory, it is dynamically created and destroyed. but it's at the end of the day a statically allocated buffer. So I'm just going to keep my drawing here of this fixed length, this dynamic thing. So that is technically still another option though. But just out of my curiosity, the thing I want to look for now is there must be some points in the code in user space or something that is repeatedly calling sock write with appropriately sized buffers. And this seems to be like the only call site, I think. File write. So this is still in the kernel, but then here they dispatch based off of the actual type of the file. And this is like unrelated stuff. And then now here is this thing. So it still must be higher level than this. Where is file write called? Or maybe somehow they can just ensure that no more than 2K is ever passed in one of these socket calls. That's also kind of a cheap solution. You just see what the maximum buffer size generally is of what you're trying to send. This seems like this, and then here's the syswrite thing. Interesting. So maybe that's enough of a dive into this. So another solution could be, just to flesh out this, it would be on every syscall dynamically allocate buffer copy in user space buffer enqueue into tx ring, and then free old buffers when reusing tx ring descriptors. The other option, which is also kind of simple to mention, is just simply increase the 128 byte limit far enough above what user space writes. That's pretty easy. The trade-off, the downside consumes a lot of memory, of statically reserved memory. That's a little bit unfortunate, but maybe we can live with that for the moment. All right, so where were we? So we were talking about this interface, about different ways we could improve this. But let's take a look at this glue code and see what this looks like. Maybe first, let's just see the code we were supposed to implement. But after a 20-second break, stand up and stretch. Okay. Net output.c. So we have a function. And basically seems like in a loop, we just need to be reading packets from the network server and sending them to the device driver. Who calls us? Serve.c. Right, serve.c is calling us. So, okay, so serve.c, this seems to be the main network server component. It's this white block, and it forks some helper processes as part of its boot up. Like this. So fork off. And then it just calls them, and if they ever return, whoa, lightweight IP requires a user threading library. Wow, what? So do we have a user space threading implementation in this OS? Wow. It would sort of seem like that. And you need to implement, I don't know, some functions or something. But where is this malloc coming from? We don't have a malloc. Or did they have to implement one? It seems like they also needed to implement a set jump. At some point, I feel like there needs to be some JOS calls. I don't know. So far, this just seems like purely manipulating local data, even thread yield. Context. Set jump. I'm not seeing so much there. Where is malloc coming from? Since when is there a malloc? Oh wow, there is a malloc in the OS, but it's a user space one. Okay. Okay, so there's like this small malloc. Okay, and it's backed by some JOS system calls. But the only system calls that are made here in this thread.c thing, sysarch. Okay, this is pretty intense. It's like some mailbox semaphore implementation. Okay, that's kind of wild. Okay, but we were just focused on I still can't believe this thread create. What is that? How is that implemented? But I guess, wait, okay, yeah, so it's user space threading, so the kernel is not really involved with this. It's just purely, it's just pure user space controlling of its context switching, which I suppose you can just do with set jump and long jump. I never really thought about that before, but I suppose set jump and long jump are perhaps all you need to do this. So that's obviously why we're not seeing system calls, is because the system is not involved when you're doing user space scheduling or user space threading. Anyway, okay, so there's like no code here. So we need to read packets from the network server and then send packets to the device driver, and the reading packets from the network server involves this IPC thing. Let's take a look at what the network server is doing, in particular with this, these IPC messages. So I'm just going to, well, I could grep for it, but it also tells us where they are. It's in this gif.c thing. And I don't know what this is, but I'm going to assume it's part of lightweight IP. That's like the portable part of it, where you need to port this to your OS now, or to your system. And here's where we see the system calls, and in particular the low-level output. This should do the actual transmission of the packet. The packet is contained in the pbuf that is passed. This pbuf might be chained. And here's where it does the user space IPC thing. So we allocate a page for our shared memory. Not sure what this GIF stuff is, but here it is, the oversized packet panic. So that might be good to lean on. We can maybe lean on that and just increase our buffer size pretty huge past this, and therefore we will be guaranteed to never be given anything larger than this. Okay. So it send data from the pbuf to the interface, one pbuf at a time. Yeah, there maybe is some linked list activity going on here, something like that. That's why it has this local cursor kind of thing going through the linked list and copying the payload into the transaction buffer at a size that is being incremented. Interesting way to do this. Instead of doing an addition, but whatever. Okay, cool. And so we're accumulating all of the data into this TX buff, which is packet JP data. Packet is this, it's pointing at the shared memory region. And GIF packet is this thing that it was telling us about. So the shared memory region is this GIF packet kind of thing. Okay. JP data, okay, yep. And we just start writing from there. This thing is limited to 4K, I think, so well, we're already panicking on 2K. If this requirement were eased, we would still need to have some kind of balance checking for the 4K limit, because that's what this page alloc allocates. Okay, so after we've gone through all this linked list of packets, we copy it all into one buffer for transmission and pass that through the IPC channel. Nice. Then we unmap. The thing after its job is done. Okay, cool. So I think this is pretty helpful and tells me what I need to know. I think we can get away with just increasing the packet size. I'm curious to know where this 2000 thing comes from. It would probably be good to know what the maximum, like to have some idea here of what the maximum Ethernet, I don't know, what any relevant maximums are. Surely Ethernet supports more than 2000 bytes in a packet, right? Maybe let's just ask ChatGPT. What are the maximum transmission sizes for Ethernet? Okay, I learned something. The MTU is 1500 bytes for Ethernet, not including headers. The maximum frame size, including headers, is wow. Is that for one? Is that for one Ethernet packet? Okay, or Ethernet frame. Okay. Okay, that's interesting. So in the most simple version of this, it's 518 bytes actually, which is actually, yeah, like even less than this 2000 panic. Theoretically, we could even panic on 1518 possibly. That's kind of assuming this thing is transmitting a packet at a time. Packet buff, I think, I don't know. Is that reasonable? Maybe. Okay, that is super interesting to know. I'll copy also that in here. So that also means it's maybe also reasonable just to size these at, yeah, just like something bigger than where did I even go? Yeah. Just like size it at something greater than 1518. Let's do that. Okay. 1000, let's see. So all these things are just controlled by a couple of defines right here. So in this extremely simplified version of things, we had 32 descriptors because it seemed like a reasonable number. Actually, it seemed like in here, they had 16 descriptors. I think I might even reduce my size to 16 if that's a reasonable number. I had no idea what a reasonable number was when I was choosing this. And so if we have right, so let's say we're going to have 16 descriptors, and let's just each give them a nice round number of 2k, right? Let's do it like this, actually. So let's say we have 16 descriptors, and we'll make the total one in terms of this. Oops. So then this will be 48. And then the total for size will be k num tx descriptors times k descriptor backing buffer size. Does this compile? And does this boot? It's always a bit tricky to increase the size of the kernel so much. Panic after PCI init. Let's just test. Do we get there? The kernel does still boot. That's good, because I just say that because previously I had some experiences where adding these large global buffers to the kernel caused problems with booting. But I fixed those, so glad to see that didn't happen again. So it would appear as if this still works. So now we have this pretty generous backing buffer size, which is even large enough to transmit an entire Ethernet frame in one descriptor. So it's pretty generous. And therefore, anything the user space network stack could throw at us should be able to be supported in a single system call, assuming that user space is passing us at most one Ethernet frame. Who knows if that's true? But also we have this panic in user space to lean on, where it panics if something over 2,000 bytes was transmitted. So it should be very safe. So this 2048 should be a very safe number to use. Theoretically, there's some waste here, or even quite a bit of waste. There's like, if the max is 1,500 bytes or so, we're wasting at least 500 bytes of space that will never be used. And so we could theoretically optimize this to save some memory. I decided to do this. 248 wastes memory since the Ethernet frame max is 1518. Could optimize this to even be maybe exactly 1518, although user space only panics at 2,000. So would probably need 2,000 then. It's kind of a weird comment, but yeah. It's kind of weird that user space only panics at 2,000. It seems like it should panic at 1518, which means could theoretically be possible for user space to craft like a weirdly big packet of 1,700 or something like this. And I mean, even in that case, we have this length check in our code. But yeah, so something like this, but I'll just leave it at a nice generous 2K for the moment, just to get this working. So that was pretty easy. So now we can probably just go we can go and implement that that output helper server. Okay, got a nice while one loop. Read a packet from the network server, send the packet to the device driver. We're going to need an include here, at least. We're going to need inclib.h because we're going to need to call sys network transmit. And just curious, does this compile? That did compile, but this should not compile, right? Good. So we're able to get, because if we didn't have the header, then this would not compile, or it did compile. ns.h includes the header probably. Wow. ns.h includes what, mmu.h? No. Sockets.h? No. Types.h? Wait, okay, I have no idea how. Oh wait, okay, I was weirdly looking at something else. So this thing already includes lib.h, although I don't really know why. Because nothing in this thing really needs it, but it's probably just in anticipation of us needing it here. Maybe I'll do this thing just to be consistent. So yeah, we'll need to do this, but first off, let's start off by reading a packet from the network server, which means we're going to need to call IPC receive, and it needs a lot of stuff. So it's been a minute. So the way this whole thing works is that now we're a process. We need to have some place for the shared memory to go. This was always a little bit sketchy. I kind of, what's a good example of this? IPC, who else is calling IPC receive? That's the question. The file system server does. Some of these random user space programs do. In a lot of these cases, I think they just declare some random constants, which honestly is like kind of strange. Because then how do I choose? How do I know what a good constant is? What about here? Get buffer. But this is okay, so it seems like here they actually allocate something. I think I would like to prefer that instead. What is required? Oh, wait. Okay. They automatically, they give us a place to do this. Queues, I don't, yeah, I don't really understand where this queue size thing is coming from. And that is, I don't know, what kind of close to the top of user space memory or something. All right, 20 seconds, be right back. Okay. Okay. So I'm just going to go back here and copy some kind of example client, which this is a good one. Okay. So this is how you do this, and packet is up here. And here we are creating this union thing. NSIPC. Now what could this be? Are we supposed to use this? I kind of doubt it. What is this? Send something. Okay, I don't. Because I was just kind of planning on doing it kind of raw, meaning just directly. So what is this binary name thing? I don't really know, but so we do a receive and we get a bunch of information out. We get information about, first of all, the status of this. I'll just copy this entire thing. I think we need all of this. Whom not equal to and critically spec output. We are expecting specifically these conditions. It should only be the network server sending us specifically just these output messages. Okay. And after that point, we can access the shared memory region, which is this GIF packet thing. And what do we need to do? We need to pass two things. We need to pass packets. It's this global thing, this global pointer. And we pass it the data, pass it the len. So we don't have the include. How do we get the include for this thing? It's in Why don't we have, has no, oh wait, JP, oops, JP. Okay, and we can probably do assert that is less than or equal to 2048 at least. Driver will check this also. Well, the driver won't assert, it will just return. I don't know, something like, we probably don't need this first assert. Or maybe it's just confusing to have it, I don't know. So now we just do this assert. And we do this forever. There's no way to like gracefully bring down the system. I don't know, I'll just make to do. Is there a way to gracefully bring down the system? Do we ever exit? Currently, we don't. We just sit here forever. In order to do a graceful teardown, there needs to be a way for the parent server to somehow communicate to us that we should exit. But at the moment, I don't think that exists. So we're building a system that can only like turn on and can't really gracefully shut down. Okay. First, this is compile. Why is so much recompiling like that? Okay. Okay, I think that sort of did it though. But now I'll go ahead and make some commits. So the first commit is just to redefine increase backing buffers to 248. The max Ethernet frame is 518 headers plus data, the basic. So this is enough, this is more than enough to store that. Okay, this is like some kind of a random comment that doesn't really matter. And then we have this thing, and maybe I'll just delete the include. We have a very simple output helper server. Okay, nice. Okay, so then what happens now? So done, implemented exercise 8.
Damn, son, where'd you find this? This is a certified hood classic.
Okay. You can now use net test output netc to test your output without involving the whole network server. Try running make run test output. You should see something like okay, but I don't think that will work. because this thing is going to try to... okay, wow, it really, it forks its own output server and triggers some sends to it. Yeah, so in the way we've currently written it, it's only allowed to send stuff to us if you are a particular... Oh wait, but no, oh wait a second, no, we just take it from this parameter. So actually I think all that should be fine. So let's give it a try. How do we do this? All we do is this. And maybe it would be good to enable some of these. I think I enabled a bunch of them already. So what happens if I do, I don't know, panic, because I did a panic in the init. Let's not do that. Does this work? I think that worked. It's very noisy. This message comes from Kimu that it ultimately got something. And it seems like they transmitted 10 packets of 9 bytes each. Let's check out the TCP dump. And we got something. Check that out. I think, yeah, you should see something like transmitting packet 0, blah, 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 blah. Right, do we see this? My my Kimu prints are adding a bit of noise here actually, but yes, we are seeing the core important messages. And this outputs something, something, something packet. Okay, let's check the data. So what is it? 50, 61, 63, 66B, blah, blah, blah. 30, 31. I think it's working. I think that totally worked.
This is a certified hood classic.
Yeah, I'm gonna call that a win. That feels good. This network driver has been pretty difficult. It's going on for weeks now. So it is very nice to get through this a little bit. Although we have been stacking up a couple wins. I mean, even to get this point, we've needed to get the driver initialized and sending packets and stuff, but now we have some basic functionality of the simple output server. Honestly, it's not that hard. It's not a lot of code. It's this amount of code. It's not that hard to do it in this very kind of naive way that doesn't have graceful error handling and all that stuff. Okay, what is next? Let's just keep it moving. Just try with a larger packet count. Okay, let's do it. Net C flags, something, something. Did that work? I don't think that did anything. Do I need to do anything special to make this work? I don't think so. So it sort of seems like, oh wait, no, I did that totally weird. I need to do env. Okay, back to this. It's because I'm using fish shell, and it's somehow strange with environment variables. That also didn't work. What? If this overflows your transmit ring, double check your handling. Blah. I'm pretty sure I did that. Yeah, okay, why is that? So that problem aside, we can quickly just change it by doing this. Okay, so now this will do 100. Yep. Did that work? I think that kind of worked. It transmitted 100 packets, and it seems like there's content in them, and it seems spin for all in case our IPCs or packets need to be flushed. It actually renders some text into, no. It computes a length, but the packet data, oh wait, what? It renders some text into the packet data and then returns that as the length, I see. Oh, and oh wait, okay, so I see. This is a hex dump of the data. I didn't totally get that. I didn't really get what that text was, okay. So yeah, okay, that's totally working. What's not working is the weird define thing. And why? What could be the problem there? Verbose 1. Maybe I don't want, no. I don't want to run Keyboard, I just want to compile. But wait a sec, can I just do this? I want to do obj net test output. Can I do this? It's up to date. If I delete test output, and rebuild it like so, it relinked something. I can totally wipe it, but what if I delete the object file? No, I just need test output.o to be deleted. Now, and apparently I also need to delete this thing. So now I should at least see a GCC line. And it does seem like the D thing is going through. Test output count. I'm just gonna set this back to 9. Or it was a 10. If not, define T test output count. And it builds the file system. And I would hope that that's included. It's not a huge problem. It's just a problem with the weird build scripts. So it's just a problem because we're not going to be able to run the grading scripts now. What is going on? Why? Make run net test. So one reason is because it is not recompiling the kernel, or yeah, that's probably why. It's not recompiling the kernel. So the way this whole thing works is a lot of these binaries. All right, be right back in 20 seconds. The way this works is these user space binaries are compiled directly into the kernel as binary blobs, and they also are included on this file system image. But when we do this particular setup here, I believe it's running the programs out of the kernel, and I don't think the kernel is being recompiled. I'm just going to do a clean rebuild. I think that's going to work now. We need to be recompiling the kernel when we do this kind of thing, and there in the build system there's no dependency from the kernel onto these programs. So that this is totally working. 19, we can just make clean and rerun it to 100, and we should see that. Sort of a bummer. We don't actually need to do a clean rebuild, but we could just delete the kernel or something. But that is working. That is working. Nice. Okay. So let's do it. Let's run the grading script. As usual, I'm going to go to grade lab 6 and comment out only the things that I expect to pass. Grade lab 6. This is like old stuff. Test time, I don't know why it's so slow. Wow, it's pretty slow. Oh. Unexpected packet. Plus 92 more. I think it must be, where is it getting these things from? Let me try that one more time. Okay, I'm also going to comment out this stuff because it's kind of slow. So what do these tests do? Maybe unlink. Oh, wait. Test output, this is backed at 10, right? So, and it's controlling that anyway. I think the problem is that it is not cleaning. It's running into the exact same problem. I need to make sure to, for example, like I really need to make sure that the kernel gets rebuilt or something. So I need to clean before running these tests. Wow, this is slow. Something is taking a very long time. What is possibly taking so long? Okay, huh. All right, I'm failing the tests. 5 packets and 100 packets. What is going on? So let's really just trim it down. Oh wait. What? All right, let's take a look at test output 5. Yeah, okay, it transmitted 10 for some reason. But I have good reason to believe that that's not a problem with my code. That has got to be a problem with the testing scripts. Right, there's 10 things here, yeah. I think the problem... What? Also, why was it taking so... It's so weird why it was taking so long. If I really just comment out everything, but that single test 5 thing, if I make clean before I do that, there's like nothing there. Grade lab 6. Help? Verbose. It's triggering a build, but is it doing it correctly? I think it must not be. I think it's this whole fish thing. If I go to bash, make clean, I think if I do this exact same thing, it will work now, because it is not passing the environment variables correctly. Because I don't know what the issue is with fish. I think you need, in like my experience, you need to run env first, but that didn't help me either. What? Okay, these are the worst kinds of problems to debug. Our user test. Maybe unlink, save pcap on fail. net C flags D. So just to be clear, clean, and I was doing something quite similar, right? Let's say if I put a 5 here, is that kind of similar? Net flags, right. Yeah, so that totally only did 4. Clean. It is just not getting the environment correctly. So I just want to see what kind of like command lines it's running here. Run Kimu, run blah blah blah. Maybe unlink it. Huh. It actually unlinked the kernel, which should cause the kernel rebuild. So yeah, I'm not sure what was going on there. So what I want to see are the command lines that are being run. So okay, back to my working situation. If I do this, well, there's a ton of output, but I can maybe yeah, I can see D test output counts as being fed into all sorts of stuff. All sorts of these net things. Oops, can't really scroll in tmux that well. How do I search in tmux? Tmux buffer. Right, so we can clearly see that this is working. Maybe in contrast, let's run a build, but let's not use the env thing. Ideally, I would only build test output and not the whole world. Output. So that like seems to not work, right? Okay, I have no idea what I'm searching through anymore. I think it went to the top of the buffer actually. Right, okay. Excuse me. Oh, okay. I think that's what's happening over here. Also, But I could have sworn, like, running in bash, I would have thought that that would help with this kind of thing. Okay, we're gonna go into bat. Oh, I see. I did not code list of JAWS. I didn't. Oh wait, no, but I am there, right? Okay, that was weird. I'm exactly where I need to be. So I'm going to delete a couple key files. Okay. Seemed like it did too. Whoa. So now we're passing, okay. Tell me what changed. I think it was just the bash thing. Let's run that one more time. I think it's just being in bash and some shell stuff. It does take a very obnoxiously long time. And now it is failing. Ah, it passed the last time because I compiled it with, I specifically in my fish environment compiled it in a way that it was working with test output with the D thing, and then when I ran the test, it just needed to recompile everything else around it. So what I want to do now, if I can, is search back for test output. And we can clearly see here that there is no D test count in sight. That's what it's called, right? D test output. So now, make, I want to find I was looking for a make command. I'm not actually. I think I need to run it in verbose mode. It was a -v, right? -v. Let's see everything. Test output. So we see it right there. And that's the only instance in the tmux buffer, apparently. If we search for something else, like test output, we would see a bunch of matches. So clearly, that is not working. I might need to patch something here. The easiest thing would be if there is some kind of command line. Make args. Where are these make args used? Here. Here's the command. So what we want is something different. Wow. Okay. My command is going to be different. I'm going to run env make args this. I'm just going to run it in a different spot. And I'm going to hope that that fixes things. Let's see. So that didn't work, but maybe I can already see in my history. Okay, no, I'm not seeing a command line that includes this critical string. It also seems like the end. Okay, well, maybe I should. Exec must contain only strings. What does make args? Oh, dang. Okay, I need to. I don't know. Make args is. No idea what make args is. Cannot concatenate string and tuple. Is make args a string? Make args. It's a list. This popen thing, what is it? It takes a list, right? What if I converted it to a list? Print. Just watching stuff compile. It somehow transforms into a tuple along the way. Okay. Okay, that's weird. Make S no print directory. Yeah, it's kind of a lot of effort I'm spending right now just to fix these stupid scripts. Maybe that is a bad idea, but it is kind of nice to be able to run these tests. Show make args. And the problem. Okay, here is what I'm going to do. This is going to be awful. I'm going to do list and convert the tuple to a list, and then furthermore, I'm going to only get the first one. Where was that? I only want I don't want the index 0, which has this weird run test thing. I need that actually at the end. List make args worst code ever. Okay. And I'm kind of hoping that this will properly run. Oh, this last thing needs to be a list. Okay, almost there. That's pretty sad. It still didn't work. Test output. What I'll search for is I want to see where this thing gets compiled, which is right here. Just like somehow that variable is not making it in there. That D, this, like, so is there a way I can hack this somehow? I need to control this, like, compile flag. It all happens right here. Maybe the problem is this weird vars file somehow. Yeah, why? Yeah, kind of unfortunate. There's so much compile noise going on here. Let me just see. So if I once again search for test output, we go and we find where it's getting linked into the kernel. We also go and find where it's actually just being compiled. What's the next thing? The next thing is the previous failure. So from here, I am trying to find some make command, but I also don't even see one. Okay, I am sort of running out of time to just keep fiddling with this infinitely. So now it's the time to look for any absolute dirty hacks, any possible dirty hacks we can just pull out of here. Any other way we can seriously just like hack this? I kind of want to just see what the command thing looks like. No execute GDB, Nox GDB, don't really know. Where is that specified here? Test, no. It appends some Nox GDB string somehow. And just somehow this, but it seems like this is running after things get compiled. Is that possible? These are just helper functions. Did I comment out something important, maybe? Basic tests? No, I don't think so. It's time. But I think this did work though at one point. So it's like it's pretty odd that these scripts are breaking so horribly. It's kind of unfortunate. It would be nice, but maybe it's not important. Maybe the further tests don't actually rely on all of these like defines and stuff. Count, how is count used? In the future tests, it literally uses Python to communicate with Kimu or something like that. So there's no conditional compiling. And I don't think there is any more conditional compiling here either. We can just easily find it by searching for make args. It is very weird though that make args was working for the PCI stuff and this other stuff, but was failing. I think I have an idea why things no NS. Never mind. Okay. Yeah, it's kind of disappointing, very weird. Not very valuable to spend a lot more time on though. So I'm just gonna call that a win though. We clearly got the core functionality working today of being able to transmit data using the output helper server. And that's pretty cool. And then let's just take a look at what's next. Okay, question, how did you structure your transmit implementation? In particular, what do you do if the transmit ring buffer is full? I don't do anything. I just drop it. What could I do instead? maybe I could wait and try again. The part of the code that's relevant is sort of here. I mean, there's multiple places. Well, actually, no, it actually is just right here. This is the part where we realize the buffer is full. And I don't really know if that should be handled right here exactly. I think it's correct to return an error, but then the actual syscall could decide what to do. There's maybe some other options for what to do would be to... Okay, another, just a totally different semantic would be to like completely block the system call until we can write it. In which case, we would basically just keep retrying. That would not be that hard to implement. We would just keep retrying. We would, and like the system call would just do a loop of like just calling this until it succeeds, or maybe you can consider some amount of maximum number of times it tries or something like that. Some like even, or a timeout or something like that is also a possibility. But in terms of the two major decisions of how one could go here, one way would be blocking, one way would just be simple non-blocking return a failure. And that's just what I did. So it seemed pretty simple and just something you could push off to higher in the stack potentially. So at the moment it's pushed all the way onto user space. User space is the one that needs to retry if they like some number of times. And I guess that would actually just be in the output server. So could consider retrying also in case of failure. So currently we actually crash if the buffer is full, we assert. And maybe that's actually wrong to do. Well, what are the other reasons this could return? It's only if the buffer is too big, and if so, yeah. So this thing, yeah, so it's actually valid for it to return in case it was too big, but if it returned too full, it's probably not correct to, I don't know. Of course, we could have some defines or something. Assert that it's not too big. First produced should never trigger. Oops. Oops. Here, the size check. And then something like if red equals -2, or even like a do while or something, I don't know. Retry some number of times. I guess those would all be options here. And yet another kind of option, if we really wanted to try to make this work, is to have a second buffer and like internally buffer it into this other queue, which then gets emptied into the main queue. But that, I don't know if that's better. It sounds kind of complicated. having these two levels of queues, like, yeah, I don't think that's actually better. I probably wouldn't do that. So I think that's my analysis of the different ways one could have structured this. And we'll leave it there today, and next time we'll keep it moving with part B, receiving packets. All right, I think that's going to be it for today. Thanks a lot for watching. I'll see you next time. Peace.